Okay, class, we are now on 11.1b. This is molarity. There are several different ways to describe concentration, and each have different applications. In this last lesson, we described concentration by percent and by fraction. In this lesson, we will look at a third way to calculate concentration called molarity, and this is the most, molarity is what tends to follow you through the other sections of chemistry that you need to take. When describing chemical reactions, we are frequently concerned with the number of moles of a substance that are consumed or produced. In these cases, it is helpful to express concentration in a way that allows us to quickly convert to moles. Because of this, chemists often describe concentration in terms of molarity, which is capital M, which is the moles of solute per liter of solution. We commonly write this in an abbreviated form of M equals moles over V, where V is the volume in liters. The molarity equation also allows us to find the number of moles present, given the concentration and the volume. Since molarity is equal to moles over volume, we can rearrange the equation to solve for moles. So let's do a problem. An aqueous solution with a volume of 9.41 liters contains 412.3 grams of dissolved potassium chloride. What is the molarity of this solution? So first of all, in order to solve this, we must convert the amount of potassium chloride from grams to moles. The molar mass is 74.55 grams per mole, and we set that up so that we can get the moles of potassium chloride. Now we can set it up with the liters that has been given to us in the problem. And the answer is 0.588 molarity of potassium chloride. Okay, so let's look at another one. How many moles of HCl are in a 250 ml sample of 6 molar HCl? This is not a difficult problem. This is actually a very easy problem. You just have to make sure you understand the equation for molarity and then plug in each thing that is designated where it needs to be. So we want to know the how many moles. So first of all, we have a volume, but we can't use milliliters. We need to change it to liters. Once we have that, we can change the equation to isolate for moles, and we have the molarity per volume. So when you're doing the problem, don't use the big M, use the moles per liter so you can see what things cancel out. And it cancels out the volume, the liters here, the liters on the bottom, and it ends up producing 1.5 moles of HCl. That is the amount of moles that are in a 250 ml sample of 6 molar HCl. So now we're going to move on to something a little bit related to it. So here's a question. If we dissolve 1 mole of sugar in 1 liter of water, do we have 1 molar of solution? No. Because the sugar also takes up space, the volume of the solution after mixing would be more than 1 liter. The solution is almost 1 molar, but not exactly. So how do we prepare solutions in which the molarity is precisely known? So let's take a look at this. To prepare solutions in which the molarity is precisely known, chemists routinely use a 3-step procedure. Measure out the desired amount of solute and add it to a volumetric flask. So in this case, think of the potassium chloride. Let's say that we want a certain amount of moles. So we would figure out how many grams of that, and we would put this into the volumetric flask. Particularly, fill the flask with solvent and mix until the solute completely dissolves completely. Dilute the solution, slowly adding solvent until the correct volume is reached. So for a volumetric flask, you can only have certain amounts. So this volumetric flask, let's say this is 100 mils. It has a line, and you would add in the solute, you would add solution and invert this. So you would have a lid on this and shake this up and down and have it dissolve. Once it's fully dissolved, then you would fill this very carefully to where this line is at eye level. And that's going to give you the amount of that you wanted in 100 mils with whatever the molarity is that you needed. So by following this procedure, the amount of solute and the volume of solution are both measured precisely. Many laboratories store common chemicals, such as acids and bases, as concentrated solutions. While this saves space, chemists often need more dilute solutions for routine use. So for instance, if they have a strong acid they tend to store strong concentrated acids and then dilute them as they need them. So then in that case, they can they have just the big bottle and they don't have many other bottles of dilute solutions. They just use it when they need it to make the correct molarity that they need. So if we need a dilute solution, say 1 molar of aqueous HCl solution, how do we prepare it from a concentrated 12 molar solution? So let's say you have just a 12 molar solution. Chemists prepare dilute solutions by mixing the concentrated solution with additional solvent. So think of it like those punch bottles that are really concentrated. You take it out and then you make the amount of punch that you want, matching the taste that you want. So you would add a certain amount of that red liquid punch to water until you get the consistency that you want. That's the same thing here. So we want to mix the concentrated with additional solvent until you get it to whatever it needs to be. Doing this increases the volume of the solution, but the moles of solute do not change. That is, the number of moles of solute in an initial concentrated solution is equal to the moles in the final dilute solution. Think about diluting an orange drink. If you begin with a concentrated solution, then add more water, the volume changes, but the amount of dissolved drink does not. Since the moles of a solute is found by the molarity times the volume, we can rewrite this expression based on the molarity and the volume of the initial and final solutions. This is where MI, I learned it as M1V1 equals M2V2, but it's the same thing. I, it stands for initial, F stands for final. You might also see this as C1, CIVI equals CFVF. And that just stands for concentration instead of molarity. They mean the same thing. Where MI and VI are the initial molarity and volume, and MFVF are the final molarity and volume. Using this relationship, we can prepare dilute solutions of known concentration. So let's plug in this equation to do a problem. So you have 25 mils of a 100 ml solution of potassium hydroxide. To this you add enough water to make 500 mils of a dilute solution. What is the molarity of the final solution? So to solve this problem, we begin with the dilute relationship, which is MIVI equals MFVF. In this problem, MI is 10. So the best thing I can tell you is pull everything out of it and assign it to whether it's part of the initial or the final, and that will help you understand the problem more. So MI is 10 molar, VI is 25 mils, VF is 500 mils. We're trying to find the molarity. We therefore arrange the equation above to find the final molarity, then substitute the values in question. So substituting the numerical values, we get 10 molar times 25 mils over 500 mils. Because we want molarity, we expect the units of volume to cancel out, so they have to be the same. So in this case, we should make sure that you should pay attention to, are you ending up with the units that you expect? The milliliters cancel, giving us a final answer of 0.500 molar potassium hydroxide. Notice that although we need to convert the volume from milliliters to liters in order to solve for the moles present, we did not have to convert the volume units to solve this problem because the units cancel each other out. So in this case, they canceled out, so we could leave the mils in it, knowing that it was going to cancel and give us the molarity, which is what we were looking for. Starting from a 12 molar concentrated HCl solution, you need to prepare 180 mils of 1 molar aqueous HCl, hydrochloric acid. What volume of concentrated HCl do you need? So in this case, it's the same. Make sure you pull out what's the initial, what's the final, and then solve the equation. Isolate the equation first before you plug everything in. So in this case, we have 1 molar times 180 mils over 12 molar. Now the molars are the concentration is going to cancel out, and which is what we want because we want the volume, which we can leave in 180 mils in this case. If you're not comfortable with it, put it into liters if it makes you feel more comfortable to doing that. So in this case, the units of molarity cancel out, so it's not necessarily necessary to change the volume from mils to liters. We use milliliters for the volume, and we're left with milliliters of volume in the initial. So here's a summary again. We have molarity. You can solve for anything with molarity. You can solve for the molarity, which is moles over volume, which tends to be liters, moles over liters. If you want to solve for moles, then you would just separate this, or you can even solve for volume. So you can move this around any way it needs to be. So let's do some problems. Convert 52 mils to liters. I did not do the conversion here because by now you should be sort of comfortable, or hopefully very comfortable, in seeing this and realizing it's not that difficult of a problem. How many moles of solute are in 87 mils solution of 3.10 moles of lithium chloride? So this is molarity. Remember, when you have big M, that just means moles per liter. And if you need to write that out to feel more comfortable to see what needs to be done, then you can. In this case, you need to get out of mils. We only don't have to cancel mils usually when it's in dilutions. This is not a dilution problem. So in there, we have to change to liters. And then, so here is a conversion to get this to liters. Then the liters cancel out. And it tells us that there is 0. This is my calculator. I did not round on purpose, so you can see my calculator answer. And there is 0.270 moles of solute in 87 mils of a 3.10 molar lithium chloride solution. A 100 ml solution contains 15 grams of magnesium chloride. What is the molarity of the solution? This is a very easy one because remember, molarity is moles over liter. So you're giving magnesium chloride. All you have to do is convert it to moles, which we did. And then what I did is I converted the milliliters to liters, which is what you see on the bottom. Again, I purposely didn't round so you can see what the answer and how I got that. What is the molarity of a solution made by dissolving 25 grams of sodium chloride in enough water to make a 100 ml solution? This is similar to the problem that I just did. I got to moles, plug it in, convert to liters, and my molarity is 4.28. What mass of HCl is present in 250 mils of a 6 molar solution? Now, this is not a difficult problem. However, you're going to have to change things around in order to determine what the mass is. Since we don't work with mass right now for molarity, we need to get the moles and then convert to mass. That's the only difference that we're doing here. So we're going to take the moles per liter. So we have the 200, this is volume. So it's liters. We have molarity, break it out, so moles per liter. That cancels out, which gives us moles. I actually just threw in the additional step of doing the molar mass of HCl, and that gave us the amount of mass of grams that we would need, or what would be present in that. Okay, so again, preparing dilute solutions, moles initial equals moles final. The moles don't change, it's just the volume. So your lab has a stock solution of 12 molar hydrochloric acid. For a set experiments, you need 2 liters of 1.5 molar hydrochloric acid. How would you prepare this? So this is very similar to when I was showing you the picture. You use a pipette to transfer 200 mils of 12 molar stock solution to a 2-liter volumetric flask and dilute it to the mark. So this is very similar to what I was just saying, where you add it, you add volume, you make sure it's dissolved, and then you fill it directly up to that line. How much water must be added to 25 mils of a 6 molar HCl solution to make 1.25 molar? So you have 3 variables here. You have to figure out which is initial, which is final, and what's being asked. So it's asking about water. How much water needs to be added to that concentrated amount of HCl to make a certain amount of HCl. So I just kind of put everything in without isolating it out, but you can see what the initial was, where the final is, and you can see what the answer is here. 120 mils is what you would need of that, of water. How many milliliters of 15.6 molar nitric acid are needed to make 500 mils of a 3 molar nitric acid solution? So again, figure out what is the initial, what's the final, and then plug it in. And that's telling you need 96.15 mils, which rounded down is 96 mils.